Okay. Explain what is the greenhouse effect. So we're looking for the definition or the explanation of that process, the greenhouse effect. Kathan? Not exactly. It's got something to do with the gases, but not necessarily the ozone layer.
The greenhouse gases trapping heat in the atmosphere and cooling it down on the Earth.
Yep, that's true. So the greenhouse gas overall does what to the Earth? It makes it... Okay, it makes it warmer, heats it up. Luke? Yeah, good explanation too. And one way... Oh, go ahead, Trinity. No, please. Ladies first. Well, the effect goes up with more carbon dioxide. Is that what you're saying? Okay. So it kind of works like this. You know how, here's the simplest explanation I can give. Like a warm summer day, it's kind of hot out. It might be 80 or 90 degrees out, but your car has been sitting in the sun, and you go to get in your car, and your car's like 150 degrees. It's like unbearably hot in your car. Why is it that your car is hotter on the inside than it is outside? Something's happening. Kathan?
Well, the sunlight is going through the window, except it's not really going back out.
Okay. Yeah. So basically, he's right. Light is kind of neat in that it can transfer energy without really losing any energy. It can like go through the atmosphere and not lose any energy. It can go through your car window and not lose any energy. It goes into your car when it hits something, like your seat or the dashboard or whatever, it gives off its energy and makes it hotter. And then that glass that's in there, it allows the light to come through and bounce out, but it traps the heat inside there, so it actually gets hotter inside. And that's an example of the greenhouse effect, is your car is way hotter on a sunny day than outside is. And the Earth has the exact same thing happen. The Earth has, our atmosphere acts the exact same way. Light comes through it, doesn't give it off, and then when it hits the ground, the light gives off its energy and makes it hot. And then that atmosphere that we've got, traps all that heat in, makes it warmer. So that is the greenhouse effect. Can you explain how it might be a good thing or a bad thing, like what that could do for us? Mr. Jimmy?
There's too much gases in our atmosphere, then the greenhouse effect would go too much.
Okay.
It would trap too much heat.
Which would mean that it
would warm our Earth too much.
Yeah, so there's one way, right? Too much of it would warm our Earth too much. And I'll give you an example of a planet in our solar system that has happened in. It's called like the runaway greenhouse effect, where scientists use it as an example for what's gone wrong. And then we're going to...
With all the heat being trapped in there, melt the glaciers more than they already are.
Yeah.
And it'll increase the water level, which will cause more floods nearby.
True. So and on the other, so it's good. You guys know the story of Goldilocks and the three pigs or whatever? No, that's not it. So Goldilocks is walking through the forest and there's a wolf chasing her, so she's got like a red hood on. And no, it's not. Do you have a 2-year-old? I didn't think so. I read this to my 2-year-old every night. So you don't have a 2-year-old. You know a 2-year-old. So in any case, Goldilocks is running through the forest, getting chased by a wolf with a red hood on, and she runs up on 3 houses trying to get into the houses, and so she blows on one of them and it falls over, and then she blows on and it doesn't fall over, so she goes in the middle one, and in there is porridge, but there's 3 bears and they're asleep, so she eats their porridge, and one of them's too hot, one of them's too cold, and one of them's just right. No. Yeah, and then she has to let her hair down to get out. Yeah, I forgot. Thank you. So, the point was of Goldilocks and the 3 pigs and the houses she tried to blow down and the wolf with the red hood that... No, it's the story. I know. No, I know this story. I know this story very well. When I want your idea of what the story is, I'll give it to you. But for right now, I know what the story is. So, anyway, like I was saying before I was so rudely interrupted, was that In that story, the gist of it was there's like 3 bowls of porridge, right? One that's too cold, one that's just right, and one that's just too hot for her. This is an actual term that astrophysicists use. The Earth is in what's called, maybe you've heard this before, the Goldilocks zone. Have you heard that term before? Yes. Means that we are, there's like the right distance you got to be away from a star to like have life on you. If you're too close to the star, it makes your planet too hot. Liquid water can't exist because it's steam and it's too hot for life to happen. So there's like the too close zone. There's the zone we're in, which is called the Goldilocks zone, where it's not too hot, it's not too cold, it's just right. And then if you get too far away, you're in the too cold zone. So there's this place, and it's a distance away from the sun that's called the Goldilocks zone, and our planet happens to exist there. And what the greenhouse effect does is it keeps our planet just right. If it's too cold on our planet, all of our liquid water becomes ice, and that can't support life. As best we know, that can't support life. So it's important that we have the greenhouse effect, because without it, it'd be really cold. Like, how cold is space? What's that? Yeah, like absolute zero.
It's actually, it's like, I know it's like in the, like, maybe 36,000 or million degrees.
Nah, it's like negative 273 degrees Kelvin, I think is what it is. Or Celsius. Yeah, it's a little warmer. Yeah. So I'll give you an easy way to remember how cold it is in space. You guys ever see Austin Powers? Right? You remember when Dr. Evil goes into space on the thing with his cat, and they're in there freezing, and he goes, "It's frickin' freezing in here, Mr. Bigglesworth." That's how cold it is in space. It's frickin' freezing in space. If we did not have our atmosphere around us, it would be frickin' freezing here. Because that's how cold it is in space. Our atmosphere is what keeps us warm. If it weren't for that, we'd be really, really cold, like Mr. Bigglesworth and Dr. Evil in outer space. But because of that, it keeps us warm. Just warm enough. If we have too much of that, so that's how it's good. If we had too much of it, it'd be way too hot. We wouldn't have liquid water. Because if you think back in time far enough, there was a point when Earth didn't have liquid water. The Earth's surface was so hot that everything just steamed up. So there were no oceans or anything. It was just really humid. The Earth used to be that way. And that's the danger that the greenhouse effect has. If we didn't have it, we'd be freaking freezing. If we have too much of it, we'd be too hot and we couldn't exist. So it's kind of like a delicate balance. Too much of it's a bad thing, too little of it's a bad thing, but we need just the right amount. And that happens to be where we're at right now. We're at kind of just the right amount. Right? And it naturally fluctuates, goes up and down, and that's why we have ice ages and warm spells and stuff like that. But that's the idea behind it. That's what it is. It's a process that keeps the Earth warm because our atmosphere traps heat from the sun. It's good because it keeps us warm, but it could also be a bad thing if there's too much of it or not enough of it. I'll give you one last example to show you how like light passes through our atmosphere and doesn't give off heat till it gets to the ground. Did you know that, well, it rained down here this weekend? Did you know what it did up at Crater Lake? No. Why would that happen? They're both on the ground. Why is Crater Lake getting snow and we're getting rain? Go ahead, Aaliyah. That's true. What about being a higher elevation makes it snowy up there and rainy down here?
It's close to like space, I guess, so that it gets colder because it's higher up in the atmosphere.
Yeah, it's higher up in the atmosphere, which means that most of the ground, right, like we're on the ground right now, most of the ground on Earth is low to the sea level, or lower to the ground, or that's far from a bigger distance from the ground. And as a result, most of the sun's energy hits the ground where we're at, so it stays warmer here because the ground heats it up. And up there, even though it's close to ground, it's not close to all the other ground. So when the wind blows, cold air just blows over it because the sun doesn't give energy to that like it does to the ground. So, it's an important thing because in our most recent election, we had 2 presidential candidates who had 2 very different views on the topic of climate change. One of our candidates, who shall remain anonymous, believed that it is true and happening, and the other candidate, who shall also remain anonymous, believed that it is a conspiracy propagated by the Chinese in order to slow down our industrial production. So, it's important to understand the argument of climate change so that when faced with that decision, you've got the knowledge to overcome maybe somebody else's ignorance or to present them with facts instead of, non-facts. And one of the biggest ways that people confuse this is with this idea of climate versus weather. And I'll give you an idea of what I'm talking about here. You know how it can be rainy one day, like today, and then tomorrow it might be warm?
Yeah.
Those are weather events. Climate is something else. So we're going to try and figure out the difference between climate and weather, because that's the biggest difference that we're talking about. The biggest reason people get confused about this. So the first stuff that you want to get down is that the difference between climate and weather, and I'll try and explain it to you as well. But it says climate is weather over a long period of time. As in, like, in Grants Pass, the average temperature is 62 degrees. Meaning that over the course of a year, or over the course of 10 years, it averages about 62 degrees here. That's part of the climate of Grants Pass. The weather, on the other hand, is day to day. So the weather today might be it's raining out. Because it's raining out today doesn't mean it's going to be raining out tomorrow. But weather varies like day to day. Climate, kind of over a long period of time. You're getting this down, right, Kathan? Yeah. Huh? Yeah. With my non-moving hand that's attached to not a pencil and is clearly... Yeah. He writes via telepathy. So climate, that's a long time thing. That's like averaged over years or decades or centuries. And little changes in that are what we're talking about when we talk about climate change. But a lot of times what people will say is like, and maybe you've heard this before, like, oh, it snowed in the valley. That proves climate change isn't real. It snowed in our valley. How can the earth be heating up if it's really cold here? And you think, yeah, that's a great point. But the difference is that that's weather, and that's like day to day, and that can fluctuate a lot. And climate is like something over a year, or 10 years, or 100 years. And that one snow day in like 100 years might not be that big of a deal, because it's one day out of 365 in a year, or 3,650, however many in 10 years. With leap years, I lose track of that. So this guy, if you haven't seen him before, he kind of, he's a satirist, or a guy who does satire. If you know what satire is? It's a form of comedy where you kind of make fun of people by playing up their views, kind of. Like, in any case, you'll see it. But this is from a couple of years ago when they had huge snowstorms in Washington, D.C., and at that point in time, all the congressmen were in front of Congress, like, having snowballs in their hand and saying, see, I've got a snowball. The earth can't be heating up because I've got a snowball in my hand. It's impossible. It can't snow here in Washington, D.C. So this guy kind of takes a whack at that and explains why that's not the case. So as you're watching this, what I want you to pay attention to is the arguments he makes, and then when we're done, we'll get some differences. I'm going to have you guys kind of pair up and get some differences between climate events and weather events after we watch this little clip here. You can see the difference maybe between what he's talking about. When people say, like, it's snowing, it's got to be the end of climate change. And he says, well, no, that's just like what's happening today. You got to average it over a year. He said, if that were true, you'd have to look at every time it got night, you'd have to think that the sun was destroyed and that it was never going to come up again. Because if you only base the future on what's happening right now, you'd be wrong all the time. You got to look, years back. So what I want you guys to do is come up with, at your table groups here, 3 examples of like a weather event, like this would be considered weather, and 3 examples of something that would be considered like a climate thing. Make sense for you guys? So 3 of each. 3 things of weather, 3 things of climate, and I'll give you, like a minute. Examples of like a climate issue. Jordan?
So, the average temperature raises by maybe a couple degrees in the span of like a year or so.
Okay, so climate would be the average temperature would work for that. So I like that. That's good. Tristan?
It's like cold.
No, not exactly. We'll get a couple here. What'd you come up with?
I said like for the climate organ would be like mostly cold.
Mostly cold. All right. What'd you come up with, Ashley? Okay.
Spring.
No, that's a season.
It's like the rainforest, it rains all the time.
All right. So yeah, you could talk about like how in the rainforest it rains a lot, or it's humid in the rainforest, like it's always kind of wet out there. You could talk about in the desert how it's very dry and arid all the time. That's a climate thing. You could talk about how on the East Coast it's usually humid. You could talk about average rainfall, average snowfall. All those things would be climate issues. And the distinction there that's important is that climate is stuff that's averaged over a long period of time, happens over many years, and weather is like a day-to-day. So it's easy to do what those guys on, like the guys, I know that Stephen Colbert always picks on the people on Fox News, so all those guys that had little sound clips were from Fox News. But they all kind of were mixing up the two terms and saying like, hey, it's snowing today. This proves that the earth isn't getting warmer. And people who are kind of in the know would say, no, that's just the weather, man. That happens. That's a natural thing. And just because it's snowing today doesn't mean it's not going to be warm again. Doesn't mean it's going to snow forever. That's what they're talking about there. And that's why he kind of made that joke about when the sun goes down. If you believe what they're saying, when the sun goes down, you'd have to believe that the sun's been destroyed because you can only predict the future and what's happening right there in front of you. It's the kind of joke he was making. So big idea there is the difference between climate and weather. So you've got to get that part down. This next stuff we'll talk about talks about the greenhouse effect, like we talked about at the beginning here. And it's got some illustrations to kind of help you understand it. So, again, you're taking notes on this, but you're going to take notes based on what I say, not what's written. Because with this stuff, there's nothing written. So here's a picture that's going to pop up for you. And this is kind of a cool picture. Number one, because this background that you see here is real. And all those little things that kind of look like splotches or stars or whatever are actually whole other galaxies. So things that are made up of like 1 billion other stars or 4 billion other stars with planets around them. So that's a real picture that's behind it. What's that?
There's a sun down.
This thing? You would think it's a sun, but that's not. That's a whole other galaxy. That is like billions of suns in one spot. That's just so far away it looks like one like individual dot. We'll get to that. And you would hopefully, I think the probability, I watched some guy do the odds on it. The probability is that there are multiple planets like our planet out there. Yeah, this is yeah. So this, anyway, this is a real picture of out here, and then just to fix or to help Luke's mental image out here, this is like another picture of Earth that's been superimposed on it, so it's not like that. And then just to further clarify, this is not really the sun. This is just a yellow circle. Okay, just making sure. So what we've got there is a picture of the Earth, and around it, as you know, the Earth has an atmosphere, and that atmosphere is what captures the sun's rays and keeps us warm. Without it, as we discussed earlier, it'd be frickin' freezing. But luckily, we've got this atmosphere around us that doesn't let us freeze. So what happens is the sun emits light. Light, as you guys know, is energy, and that energy comes down and it hits Earth's surface. When it hits Earth's surface, it gives off its energy and heats up whatever it hits. Right, like a black car in the summertime, if you go out and put your hand on the hood of a black car in the summer in the sun, it's really, really hot. It sucks in the sun's energy, traps it there, makes it hot. Todd?
I went to Texas once, and we rented a black car, and fried egg on the car.
I'm sure the rental company was very pleased with your decision to do that. So, here at the equator, right, and the equator is halfway between the North and the South Pole, the sun hits almost directly, just because the way the Earth is set up. And what that means is it traps much of that energy. When the sun comes down, it hits the Earth is curved like that. Hits it like that, and because it hits it at almost like a perfect 90-degree angle, most of that energy is absorbed by whatever it hits. And it's land and oceans and stuff like that. When it hits the North Pole or the South Pole up here, because of the angle it hits at, it's kind of like a bullet skipping off of something, it bounces off of it for two reasons. One, the angle is a lot different. That's a very obtuse angle, right? Like a big, fat angle. Here it's a 90-degree angle. Also, it bounces off because what's the North Pole have a lot of there? Snow and snow and ice, right? What color is snow and ice? White. What's the difference between like a black or a blue car in the sun in the summer versus a white car in the summer? Yeah, it bounces that energy back out, right? So as a result, because this is white and the angle that it's at, that energy, most of it, just bounces back off. That's why our poles remain colder, partially because of the angle the sun hits it at, and partially because of the covered in ice. So we've got a warmer center of the Earth here because of the angle, a colder top and bottom of the Earth here because of the angle, and because of that angle we get, those polar ice caps at the North Pole and South Pole and whatever that we're concerned with are melting, right? That's one of the issues we've got. So what happens is we want our Earth to be a perfect temperature, right? And we talked about it's got to be just in the middle. Can't be too hot, can't be too cold. So the Earth has a system to regulate how hot or cold it is. It kind of works like this. We'll see if this happens. So energy comes down from the sun, hits the Earth, and then gets radiated back into space. That means it gets let go or released back into space. And our Earth stays the exact perfect temperature if, and only if, the amount of energy that's coming down from the sun is equal to the amount of energy that gets released into space, right? It's like a diet or something. If you so consider like the energy coming from the sun, calories, and if you take in 1,000 calories a day, but you use 1,000 calories of energy a day, are you going to gain any weight? Not even a little, right? It's exactly perfect. You're going to stay exactly the same weight all the time. And that's what we want our Earth to do. Because if we take in more energy than we let go, it's going to get hotter. If we release more energy than we take in, it's going to get colder. So we need that to stay perfect. We want to release just as much as we take in. However, what can happen is, and this is what we're worried about right now, it causes the Earth to catch on fire apparently, but we are taking in energy, and that arrow was supposed to represent how much energy we're taking in, and we're not releasing very much energy out into space. So we're taking in more energy than we're releasing, which means we're trapping more energy here, and it's getting hotter. And that's because of the stuff, the carbon dioxide, methane, and water vapor we've got in our atmosphere. So right now, we're trapping more heat here. We're holding more heat than we're releasing back out into space. So this would be like when you're on a diet, and you say, I'm only going to eat 1,000 calories a day. That way I'm going to lose weight, and I'm only going to use 1,000 calories. So you're trying to balance that out. So not a diet, but you're trying to balance it out. You're not trying to gain or lose. But instead, you eat 1,500 calories a day, but you only burn 1,000 calories a day. You're going to start to gain weight. You can think about it like a bank account if you want, where you're putting in $1,000 a day, and if you spend $1,000 a day, then your bank account stays the same. But if you're putting in $1,500 a day, but you're spending $1,000 a day, your bank account grows. That's what's happening here. Maybe we're putting in 1,000 units of energy here, but we're only releasing 500, which means the amount of energy on Earth is building up and it's getting hotter. Right? That's the idea behind it. And that's what we're seeing now. We're starting to heat up. So this stuff up here, the polar ice caps, those things are going away. They're melting, which means the poles are going to heat up quick because that stuff that is reflecting the light off of there and keeping it cool is going to disappear and be replaced by water, which absorbs energy faster than that does. So it's going to heat up at the poles. Sometimes the opposite happens, though, in our history. We wind up with energy coming down and more energy being sent back out into space than stays here. And we wind up with an ice age. Okay. And we've had those, right? We can look back, we can find those things. So that's the idea. And I just gave you two analogies. One about like calories and being on a diet. And my mom is always on these crazy diets. My mom's always trying to lose weight. So she's done like the South Beach diet and the no carb diet and the just carb diet and the just going to eat like steak and chicken diet and the basically I'm going to do everything but exercise diets. Those are the diets she does. Everything but the thing that would actually help. And she always has that complaint, like, I can never lose weight. And I said, Mom, it's really simple. It's really simple. If you use more energy than you eat, you're going to lose weight. It's like physics. It's impossible not to. Nope, that's not true. That is not true. Because if I just look at a cupcake, I gain 3 pounds. Mom, that is physically impossible. You cannot, no, and I can't, I mean, you know how it is. Even at 36, you're never going to be able to win a debate with your parents. So just to let you know now, even when you're an adult, it doesn't get any better. You can't win. So at some point you just say, whatever, you're right. Keep on the South Beach diet and see how that works. And but the point is, I gave you guys two analogies. One with money in a bank account, like coming in and going out, and one with a diet, like energy coming in and going out, and what its results are. I'd like you guys to come up with an analogy to kind of explain this process too. Like, use something other than food in your body or a bank account to explain, like, stuff coming in and not going out fast enough, and something growing or getting bigger, and the alternative, the opposite. We're going to get some ideas, and we're going to focus these on, like, Austin's group-ish, because if you guys have ever seen Seinfeld, he just played the role of Newman or Jerry, or Newman or George, and said, "There's no way you used all of them. No way, Jerry. You used all the analogies, and there cannot be another possible analogy left that any other group would come up with." And that's pretty much a direct quote, right?
Yeah, sure.
Thank you, as I suspected. So we'll start with a group that no way could ever have come up with another analogy, like right here. Nathan, what analogy did you not come up with?
So that's a trick question. Well, we did come up with one.
Oh, no way. That is impossible.
We
Physically and mentally impossible.
we thought of like the place always snowing and the sun comes out and
Mhm.
it melts half of it, and then it snows again, melts half, snows again, melts half.
Okay, so you're...
So there's, like he said, there's a place that it snows, but, like, there's nothing there to take the snow away, so day after day it keeps building up. And
Okay.
So, like,
So more snow is coming in than is
Yeah,
melting
than
off,
melts.
so it's piling.
yeah.
Right? Yeah, great. So just like this, right? More energy coming in than is going out, and it just builds up. Very good. What'd you guys... Oh, another one. Mr. Dimmick. Whoa.
If the ocean took in 1 million gallons of water a day, but only evaporated 500,000 gallons of water a day, then the ocean's water level would rise.
Yeah, the ocean's kind of in balance too, right? Hopefully, because we don't want it to rise. We want it to stay right where it is. So evaporation should equal, like, the inputs. Yeah, very good. Loving it. Let's get one more. Joe, what'd you guys come up with?
Thanks.
Go ahead, Todd.
I think you really understood it. Like, if you have an RC car and it has, like, a dead battery, and you charge the battery, and you drive it around, it dies, and that's it.
Okay, so that'd be like taking out more energy than you're putting in, because your battery drains, so you're using energy, you're not putting any energy back in, then you've got to recharge it. I'm with you. Mia, you're good? Oh, I thought you were raising your hand. Okay, so good analogies, and what do you know? There were a couple out there, and maybe some others you could think of too. I'm sure some other groups had one, but good analogies, right? That's as easy as this system works. More energy comes in than it's supposed to, the energy builds up, and the energy makes us hot. More energy goes out than it's supposed to, and we lose energy and we get cold. That's just the way the Earth works. It's called the greenhouse effect. Just like we talked about with a car or something like that, energy goes right through it. The sunlight can pass through the glass, and then it hits the stuff inside of the glass. Like the seats on your car that are like 200 or 3,000 degrees when you put shorts on and you sit in your car in the summer and it burns your legs. Like that. The glass isn't that hot, the air isn't that hot, but the seats are. So that light can go right through the glass, hits those things, and it gives off its energy, heats them up. And then that energy fills in the space inside the car, inside the greenhouse, and it insulates it. So it keeps getting hotter and hotter and hotter in there. And that's exactly what our atmosphere does for our Earth. That's how it works. There are some gases, and you don't need to get much of this down. You probably just want to identify the greenhouse ones. There are gases we have that are greenhouse gases. Gases that increase the amount of greenhouse effect that we have, and they are down here. Water vapor, if you've ever been to a really humid place, like on the East Coast, where it's like 90 degrees out and it's 90% humidity, where it means like the air is really sticky and wet, kind of like after you get out of the shower, the bathroom kind of feels wet when you're in the air because it's kind of humid. Water vapor is a greenhouse gas. The more water vapor that's in the air, the hotter, or the longer it takes for heat to radiate out of it. Carbon dioxide is the one we're worrying about. And then this last one down there, methane, is one source of methane that's probably not a humongous problem for climate change, but is still funny to think about, is farting. Because when you fart, you release methane. So not only are you causing like air scent pollution, you're causing like climate change every time you toot. And we all know like everybody toots, even though some people will claim that they don't. Everybody does, and there's nothing you can do about it. So when you're sitting there and you do your little like one cheek sneak or whatever it is you do, you're causing climate change. That's a little bit of climate change you just released. Just so you know. So now you've got two reasons to feel guilty when you do that. One, because it stinks, and two, because it stinks. You're heating up the earth. Don't do that. Just hold them in. Burp out a fart would be gross. Yeah, I don't think... Just hold them in this class. Wait till you get to like PE or something like that where you're all moving around and you can blame it on someone else. Like when you do it here, you're kind of like, you got to sit in it and then everybody knows. So be smart. Be judicious with your gas releases. So last bit I want to talk to you about today is this planet, and it's planet Venus. If you know about the planets, you know the first one away from the sun is Mercury. Yes, that's right, Mercury. So it goes Mercury and then Venus. And you would think because Mercury is closer to the sun that it would be like way hotter since it's way closer to the sun. But Mercury has no atmosphere, and it's kind of crazy. So as it spins around the sun like this, the part of Mercury that's facing the sun gets like hundreds of degrees hot. But the part of Mercury that's not facing the sun is like negative hundreds of degrees cold. So it has like 300, 400, 500 degree temperature changes every day from when it's facing the sun to when it's not. And you'd think it would be the hottest because it's closest to the sun. But it's not. And that is because Venus is. That cloud that you see around Venus, that kind of weird color that you see there, is an atmosphere that's made up of 97% carbon dioxide. That's a lot of carbon dioxide. As a result, Venus's like average surface temperature is about 860 degrees. That's way hotter than your oven can get. That's a problem. It's further away from the sun than Mercury is, but it's hotter than Mercury is because it's surrounded by carbon dioxide. Carbon dioxide traps in heat. And that's what scientists point to as an example of like, hey, this proves that carbon dioxide traps heat, and this proves like we need to be careful because the more we get in our atmosphere, the more heat is trapped in. And that's the example of it. So, was there ever a point in Earth's history when we had a lot of carbon dioxide in our atmosphere? Go back to our very first unit. Do you remember what we talked about? Was there any oxygen in our very first atmosphere? It was mostly CO2, right? And if you remember back to whatever grade they teach you this in, the law of conservation of mass, that matter can't be created or destroyed, it can only be transformed. If that carbon dioxide was once here, it's still around someplace. What got all of that carbon dioxide in our air out of the air? Tristan? Plants did. What's that process called? Actually, photosynthesis. So photosynthesis, those plants got all that carbon dioxide out of the air, made our Earth cool down as they did it. But that stuff is trapped somewhere in something we use every day. Where is all that carbon that got stripped out of our atmosphere stored right now? Not the air. Aaliyah? Not the atmosphere, because we took it out of the atmosphere and these plants captured it and now it's stored somewhere. It starts with an F. Starts with two F's. How about that? Fossil fuels, yeah. Those plants decayed without oxygen present, or without much oxygen present, and they turned into like oil, natural gas, coal, and that stuff. So all that carbon dioxide that was once in our atmosphere that helped make it so hot here is still available. And if we want to make our Earth really, really hot again, we just have to burn all that coal, natural gas, and oil, and all that carbon dioxide will be back up in the air again, and our Earth will be very warm. And that's why people are so concerned about burning all this carbon dioxide, or all these fossil fuels, because if we do that, what was once in our atmosphere will be back in our atmosphere, and it'll be really stinking hot.
So if we left our Earth alone, and let the plants naturally take away all the carbon dioxide
Yeah.
we produce, how long do you think it would take?
I don't know. I don't know the answer to that. So let's see, we're out at what, O2, is that right?
Yeah.
Okay, so I'll explain to you what I want you to do, and we'll have to get the Al Gore graph next time around. So those are your notes for the climate change stuff. Here are the questions you have to have: a level 1, a level 2, and 2 level 3s on there. So I don't know how you guys keep track of that, but however you keep track of that, you might want to jot down exactly what you got to have: 1 1, 1 2, and 2 3s. What I'd like you to do on your output page is going to look like this. It's an activity. We're going to call it "Don't Break the Bank," if that makes sense. So it's going to go on page 15 in your interactive notebook, and it's going to be 3 things. 1, 2, 3. The first one, I'll explain to you this way. You get $3. You get $3. Yep. So with that $3, you get to spend it on words. Every word, no matter how many letters, costs you 10 cents. So you've got to spend $3. You can't spend more than $3, and summarize the climate change issue that we're talking about now. Like, what is climate change? Why are we concerned? And that stuff. So if you do the math, that's 30 words or less that I need right there. Top line, top 2 lines, whatever, on page 15. Spend your $3. Give me a summary of this issue of climate change. Right under that is going to be an illustration that you make. It's got to be multicolored illustration that addresses this idea of climate change. You could talk about the energy thing we were talking about, with energy coming in and going out. You could talk about Earth heating up or cooling off, whatever. But you got to have a big illustration in the middle here. And then down below, at the very bottom part, is a short 1 to 2 paragraphs. Don't make it more than 2 paragraphs, please. 1 to 2 paragraph explanation of how your illustration and your caption up here are related to the concept of climate change. So how these 2 things kind of show what we've been talking about. So this is your page 15 stuff. And you know how I do those daily checks in your notebook sometimes? This will be the thing I'm looking to see tomorrow. You've got your questions done, your summary completed, and this thing done in your notebook tomorrow. That's the plan. Make sense for you guys? Tristan?